the next third talk of the day.
Okay, so hi everyone again. So after that great discussion, we're now moving back to high throughput processes. So our next speaker is going to be Ben Deadman, who is the facility manager at the Center for Rapid Online Analysis of Reactions, RAW. And so he's going to tell us a bit about how this facility brings together high throughput batch and flow reactor platforms, in situ technologies and automation to characterize reactions, exhibiting this with a case study in the catalytic reductive amination reaction. So over to you, Ben.
Hey, thank you. Let's get this presentation loaded up. Not like that. Share screen. Okay, share that over there. Okay.
Great.
We do it. Sound check. You can hear me. You can see me.
Yep.
Good. Okay. So yes, I'm Ben. Thank you for having me today, and thank you for the previous two speakers as well, because you've, I guess, nicely illustrated, I guess, why we need facilities like RAW. So today I'm going to talk to you a bit. Rather than being a science talk, this is going to be a talk about what our facility is, what we can offer you, with a case study thrown in to kind of demonstrate some of the things that you might be able to do. So we'll cover why we believe you need automation for characterizing reactions. We'll introduce you to what RAW is, where we came from, and we'll spend about half the time talking about this reductive amination case study. So why do we need automation for reaction characterization? Well, if you look in the lab now, you'll see we have some pretty amazing analytical tools, very high throughput LCs, we've got NMRs, all these amazing technologies in the labs now. And that's collecting massive amounts of data, and you can access, you've got all this data at your fingertips in the online literature, online databases. But if you think about how we actually run those reactions, they're still all very much handmade. Okay, there are students in the labs doing reactions on small batches with a lot of the inherent problems. And so I can see three major problems with these kind of ways of doing reactions in an academic setting. The first of these problems is the limited substrate scopes that we produce in our academic studies and we report. So if we take I guess a classic Suzuki reaction as an example, if you're going to report your substrate scope for this reaction, you will take, you're reacting a boronic acid with an aryl bromide, and you're going to fix the bromide and test it with a range of different boronic acids. And you'll go in this direction here, and change and keep trying different boronic acids until you've built up 12 or 20, depending on how good a paper you're going for, how large a table you're going for. And there'll be, there needs to be a large number of ones that work, because, you want to publish this. You can tolerate some that moderately work, but you don't want too many in there that don't work, because then the reviewers are going to shut down your paper and send it back. Once you've got that table, you're then going to go in the other direction, fix the boronic acid, and start to change the aryl bromide. And a similar situation there. You're looking to build up a set of ones that work, and you can cope with a few that moderately work. And this is, I guess, for better or worse, this is traditionally how us synthetic chemists, I'm one of these as well, I've done it before, this is how we would report our substrate scopes. And you'll use this, and we use it to infer sort of what's happening in all this space here. We haven't tested these conditions, these combinations, but it's implied based on the table of boronic acids and the table of aryl bromides which work, that these should also work. There's a large number of space out here that was never tested. There's also a large number, in some cases there'll be a number of different combinations which were tested which didn't work, and they're conveniently left off the paper, because we all know negative results are very hard to publish, and that is a problem. Okay, big data problem number two is single time point results. So you're in the lab, you run your reaction, and you leave it running overnight, okay? And how many times do we see reactions reported as overnight or 16 or 18 hours? Do we really believe they take that long? Or is it a case of, like this reaction here, it's finished at some point in the middle of the night, but no one's there to observe it. They come in the next day, they take the data point, okay? And actually, I think it's a really sad state of the chemical literature that more often than not, the reaction times that we're reporting, they're influenced by all the other activities in a chemist's life more than the actual reaction itself. You know, interruptions to have conversations, needing to go have a cup of tea, a restroom break, going home and sleeping. You know, all of these things can have quite a big influence in the reaction times we report. And then data problem number 3 is this idea of method interpretation. Okay, this is a relatively good paper in JAX as an example, and you've got the method here. And as a trained chemist, I can read this and I can broadly interpret how this reaction is supposed to be run, but there's still a large amount of room for interpretation here. And you might not want to just give this to a fresh graduate student without having a bit of a conversation about it. So there's a lot of inaccuracies in the way we report our methods, and this can lead to reproducibility problems. So those data problems again: substrate scope limitations, single time point results, and operator dependencies. So what can we do about it? Well, this is where RAW comes in. We came out of the dialer molecule network a few years ago now. We officially opened our doors in January 2019. And the idea is to place in one facility the equipment, the expertise, the software, and the training which you need to do data-rich studies of chemistry. This is all these automation tools, all the really expensive tools which is unrealistic to have in every lab. But we're trying to create a shared facility where the chemists and the chemical engineers across the UK can access these tools. And so that's our reason to be. This is what we're pushing towards, is trying to have a shared resource that everyone can use. We have a team to back it up. So many of you will know Mimi here, our director. I'm Ben, I manage the facility. We have a postdoc working with us at the moment, Alan Asana, and then we're currently rehiring a technician. So hopefully there'll be a new face to put there soon. And when you come to work with us in future, you'll either be working with me or Alan or a technician, or someone else in the future as we expand our team. And the kind of things we do, okay, I guess there's 4 major areas, 4 major capabilities that we're trying to provide to the community. The first one is high throughput experimentation tools. We also do automated reactors. Now, these are both batch reactors, but also flow reactors. We have tools that allow you to do in situ analysis of chemical reactions. That might be spectroscopic tools like in situ infrared spectroscopy, like David was just talking about, or we can also just have automated sampling. So instead of running your reaction overnight and collecting the result the next day, you can actually take samples out over those overnight hours and have a more realistic picture of what's happening. And then the final thing is analysis and design of experiments tools. The software needed and the training that we need to give graduate students to really help them get ahead in their research. So that brings me on to our case study, where we're going to show you some of these capabilities we have. Not all of them, just some of them. So this is work from Paola Farini. She was our technician, our high throughput specialist for the first couple of years, and she's now actually moved on to GSK. So she'll be working with Janelle soon, not in the US and the UK site, but Paola started looking at the reductive amination reaction because this is something that interested her from her previous research. And so we have a ketone or an aldehyde. We're reacting that with a primary amine. You've got some kind of heterogeneous catalyst in there. You have an atmospheric pressure of hydrogen. Of course, you've got a choice of solvent, you've got a choice of temperature, and you've got a choice of time. And now this reaction is actually, despite it being a relatively simplistic, not a particularly fancy reaction, is very important for a number of industries. and it actually has a large number of variables which can be optimized. So when Paula started looking at it, we kind of looked at it in detail. We decided we were going to vary the carbonyl groups here, the amines. We'll fix the solvent, the catalyst, and the hydrogen pressure, leave those as they are, and we'll also look at temperature and time, just to make the problem a bit more manageable. And Paula went away and pulled out some literature conditions and just tried those in a single batch reaction. Was very surprised to see when she takes this benzaldehyde, reacts it with benzylamine, she got 100% conversion and 0% yield. And so that kind of set us going. Why is this happening? And so the tool we use to investigate this is the Unchained Labs Optimisation Sampling Reactor. So this is a unit which sits on our high throughput platform, on one of our high throughput platforms. You have 8 little miniature stirred tank reactors. Okay, so these are the volumes of these. We can go anything down to about 0.5 mil up to 20 mils working volume of reaction. They've all got their own individual paddle stirrers. But the really cool thing about them is there's an antechamber system above each reactor. So we can pressurize this up with a reactive gas, in our case hydrogen, at 10 bar. And using the antechamber setup, we can bring a needle using the robot. The robot can bring a needle down into the antechamber, equalize all the pressures without venting it, and then take that needle down into the reaction, grab a sample, and then go out the same way. So we're able to pull multiple samples out of a pressurized vessel without losing that atmosphere. And that allows us to get some really nice data about these reactions, which we couldn't have gotten previously. And so this is the literature conditions that Paula started looking at. So we have 10 bar of hydrogen, 70 degrees. And you can see the red dots here are the conversion. You can see actually this reaction is finished fairly quickly. But you've seen the blue dots, the yield of the expected diamine product. Sorry, not diamine, secondary amine. You can see the yield drops off really quickly. And those of you who are familiar with benzylamines as protecting groups will be realizing that this is just the we're just chewing up the benzylamine group. It's not unsurprising. But the tools we have in the lab allow us to investigate this a bit more and provide some pretty nice data sets for how you might operate this reaction here, the reductive amination, whilst avoiding this decomposition product. And so Paula went ahead and tried in one run, several reactions in parallel at different temperatures. And you're able to see that, okay, if you're at 70 degrees, the secondary amine very quickly gets decomposed. 60 degrees, it's much slower. And then anything below 40 degrees, and it's fairly stable. So it's quite a really nice tool for screening these reactions in the lab. And that's the Optimisation Sampling Reactor. So based on that study, we wanted to then go and look at trying to do a more high throughput version. And this is very much work in progress. We need to do a bit more with this yet. But for this work here, we're looking at the Unchained Labs DEC screening pressure reactor. So in this case, we have 48 times 2 mil HPLC vials, all loaded into this aluminium block. You seal that up, and all of these vials are under a common atmosphere. Okay, so they have a shared atmosphere, which we can pressurize up with hydrogen gas. And into that, loaded in the different vials, various combinations of these 4 carbonyls and these 6 amines. And then these are the results that Paula got for it after a bit of optimization of the setup. And so we've mirrored the setup here. We've done every reaction in duplicate. It was actually in the very early stages of the study, what we were finding was a lot of challenges with the reproducibility. And this was actually what's made this a really useful case study for us, is the reaction is very heterogeneous. Okay, you've got a heterogeneous catalyst in there. You've also got a gas liquid interface. So as far as high throughput reactions go, it's actually quite a complex system to set up and run, really reproducibly. But we're quite pleased with these results. There's a little bit more room for improvement here, but you can definitely start seeing the trends coming out where certain combinations, and say the darker greens work really well. And then there's certainly ones like these red areas here where it's very clear the indole does not work very well. If you have the butanone, it's depending on which amine you're combining it with, it can be pretty bad. So this is a setup now. We're going to look to take this forward, expand the scope of this, and produce some more meaningful data sets. But you know, the idea is this should illustrate to you the kind of things that you can do with some automation tools to really start to collect some really good data about your reactions. So just to start wrapping up, if we go back to those data problems that I mentioned at the start, and how can we start to fight back against these problems using tools like we have in RAW. So we think about it, the substrate scope problems, we can do a lot using high throughput technologies to allow chemists the space, the time, the resource to really build out some properly comprehensive substrate scopes. We can use automation technologies to take multiple time points. Suddenly we'll get really nice multiple time point data. And then the final thing we can do is by using more machines in our chemistry, we can have interoperable procedures. Okay, if you can write a procedure so a machine can run it, then that is really clearly defined, and someone else with a similar machine somewhere else in the world should be able to run that in exactly the same way. So it just remains for me to thank our various sponsors and collaborators. Of course, Paula for running all that chemistry. If you're interested in more information about RAW, here's some details here for our mailing list, our email address, our Twitter. Sorry. Okay, our major funding sponsors, you've got the Engineering and Physical Sciences Research Council, Research England, Innovate UK, BASF have given us a lot of support in recent years. And then all these companies here are also contributing either by providing scientific expertise to our review panels, supporting us with equipment or various other methods. So thank you all, and thank you for your attention.
Thanks a lot, Ben, for that great talk. So we've already got some questions coming through, both on the chat. So for anyone else, please feel free to write your questions in the chat or the Q&A button at the bottom. So Keith asks, have you systematically tested reproducibility in your system? What is the cell-to-cell variability, and does that vary with the volume of the reaction used?
Yeah, so this is definitely something we've spent a lot of time on, and we're producing a publication at the moment to help sort of guide chemists through that. It'd be a talk all in its own. But the way we approach it is you break it down into unit operations and on the high throughput technologies, and you test them individually. So you'll go through and test how you can do the dispensers. You will test how you can do the sampling. All of these things, you test them individually. Either 12 reactions, 48, however many you think you need to do, just to troubleshoot and work out where the problems are. And in our case, we worked out the difficulty is down to the mass transfer. So everything else, cell-to-cell variability was really good on all the sampling, all the dispensing, but it comes down to how well those vials are stirred. And if you're using proper tumble stirring systems, you can get it reasonably good, but you can still get some cell-to-cell variation. And we were seeing, at its worst, plus or minus 20%. I think we're now down to plus or minus 10%. I think there's a bit of scope to improve that a bit more as well. It really comes down to the stirring. We improved a lot by changing our stir bars.
Okay, great. Thanks a lot. We've got another question continuing on the practical side from Ewan, who says, thanks for the very interesting talk. Is it possible to operate the high throughput unit under high pressure, like around 100 bars? And how about the online sampling possibility?
Yeah, so that deck screening pressure reactor, that's not a high pressure tool. That one will go up to 10 bar at high temperature. If you want to go to the optimization sampling reactor, so that's 8 reactions in parallel, then you've got scope to go up to sort of 30 bar. 100 bar would be pretty extreme. I don't know of anything out there that can do that at the moment. In terms of, yeah, and then in terms of sampling, high temperature, high throughput sampling will be a challenge. Yeah, it's just technically really difficult to do. We can do it with the optimization sampling reactor, but you are limited to 8 reactions in parallel. Or you can, open up the wallet and buy multiple robots. Unchained, if you've got the money, Unchained will sell you a system that's got multiple OSRs on one deck. So you could in principle have 16, 24 different positions, but yeah.
Okay, so I had also a sort of practical question. So you mentioned that you were looking at kind of a heterogeneous, with your OSR, it was a heterogeneous system, sort of solid liquid. Do you have anything that can work on a biphasic system where you've got, say, a water organic layer and you just want to sample the organic layer?
I think you could probably do that with the OSR as well. You've got to allow a bit of time to do the optimization. So you can adjust. There's a lot of functionality in these robots to adjust the sampling height. And it all comes down to how much time are you willing to spend developing your workflow at the start. If you're just going to do a reaction once or even one high throughput screen, it may not be worth the effort to do it. But if this is something that you're going to develop as a workflow and then use again and again and again to build really big data sets, then yeah, if you can imagine it, and you can, I think, not just imagine, if you can write down how you propose that a robot's going to do this, you can probably get it to work. But you need to be able to break it down into those operations.
Okay, and then I didn't see any other questions coming in, but I had a more kind of, I guess, a larger kind of question. So you kind of mentioned in the start, like, that this is what students do, and this is how we do it, particularly with substrate screening, that it's very limited. And obviously raw is an option to do that bigger, but it is only one facility. And as you kind of said, that you need a lot of equipment to do this. But yet it would be great to do this more regularly in organic labs around the country. So where do you see some of what you've learned from raw being taken into every organic lab?
Yeah.
And what would you need for that?
Thanks for asking that. It's a really good thing to discuss. One way you can see this working is that raw is just the start. I don't think raw is going to be the end of the automation journey for the UK academic community. I think you're going to see more and more facilities like this happening. Okay, there's already a network across the UK. You've got York, Bristol, Liverpool. We're not the only ones doing this kind of work, but the technologies are out there, and this is starting to become more accepted. We'd still like to see more of it, though, and I think there's a job there to convince the funding authorities that they should support this fully. At the other end of the scale, though, there's a lot of things we can do at the low cost end to start getting into high throughput. You don't necessarily need £1 million of robotics to do any high throughput chemistry. You can do a lot with some very simple technologies. If you were to, if you had, say, 5 to 10K, you could build a quite simplistic setup that will allow you to do liquid phase reactions. The thing that really makes the cost go up is handling solids.
Right. Yeah.
Handling solids and being able to take samples out of a reaction under operating conditions. If you take away those requirements, you can actually get into some really nice setups, which would be quite suitable for labs in general.
And what do you think would be is the biggest barrier to that beginning to be accepted? Is it just a funding, or is it a culture shift change? And training students?
Probably both. There's a funding aspect. We need to get more equipment, academic labs to pay for funding. We need to get more equipment providers to make more affordable equipment. And then the other aspect as well is there is a you might have seen this last slide I presented. These aren't yields, okay? There is a mindset shift you need to have. It's very difficult to go and report a yield for each different combination of these unless you're going to go and develop a new calibration curve for each one. So you do need to have a bit of a culture shift, a bit more of an understanding about how we collect data about reactions and the limitations of different analytical technologies to actually understand the results and embrace them, rather than kind of falling back on the old school ways and saying, well, no, it doesn't count unless it's an isolated yield. You do have to, work within the limitations of the equipment in that sense. So there is a culture change that needs to happen there.
Okay, great. Thanks for that discussion. I don't see any more questions coming up, so I'll hand back over to James for our final speaker.